Hi everyone, this is Tom Chayons with the next video in the Amiga as a Workstation series. In this video, we're actually going to be taking our first steps in building a real visualization application that we might actually encounter in a lab. In this case, we're going to be building an application that takes heat map data from a set of camera sensors and visualizes it using the Amiga. We're going to maximize the use of the Amiga screen system here to provide different sections of information in their best resolution so that we can combat the fact that we don't have as much resolution as we do, say, on a Sun workstation. And that is perfectly fine. We'll go through the process actually first of showing what the application that we're actually going to build, and then we're going to take and piece it together with me talking along the way how we actually take and put this together. I initially had intended to show how the data would be acquired from the VAX and brought into the Amiga here, but we'll have to punt that until later, until I can get something workable happening here. So with that out of the way, let's get started. We can see here, we have our Amiga workstation here, and as it so happens, I have a backup of the program that we're going to make on floppy. And we're going to take and show exactly what we're going to make here. We have the source code files in C, the .c and the .h, which actually takes and provides the data structures and whatnot. And I went ahead and actually made a little icon here for the application using the icon editor that is part of every Amiga DOS distribution here. It uses the backfill method here so that it basically takes and inverses the picture whenever you take and click on it. The nice thing about Amiga icons is that, yeah, they can be any size or size and detail that you want here, so long as they're within the 4 colors that are specified by the workbench, at least on this version at this point in time. If we take and open up the program here, what's actually going to happen, it's going to be loading the heat map data that we've saved, and it's going to be displaying it here in the lower portion of the screen with a legend on the right-hand side denoting temperature variations. We also have up here in the top section here a description of the heat map data that was captured, the timestamp at which this was captured, along with some additional information 5 minutes after cold start, and a simple description field. Each of these fields, these 3 fields, are 80 columns, are 80 characters in length. But one thing that you'll notice here, and this is something that is very unique to the Amiga as a system in the first place, what you are actually seeing here are 2 completely separate screens that have been placed on this display in a very specific way. The parts of the screen that need color and resolution have been put in their own screen right here to take and maximize the output that we have here. And since the output that we're getting here is a 128 by 128 grid array, it made sense to take and display this in low resolution so as to take and maximize the display space on the monitor. But we also have textual information that would have been very difficult to display in low resolution in its own high resolution space. This is part of what makes the Amiga a very unique proposition in terms of visualization, so that even though the Sun workstation, you have workstations like the Sun workstation and whatnot, where the standard resolution is 1152 by 900 in black and white, we have the Amiga here doing 640 by 200, but making the most of the display space that's available. And this is, of course, running alongside our other applications. So if I take and flip over, I can switch over to screens and see the other side, but I can also take and, of course, pull this screen down so that I can see the output from my heat map. It's just a very clever way to take and organize the information, and this is something that is very easy for the Amiga to put together. So with that, we've seen what the application that we're going to build here, so let's go ahead and just build it. We'll go ahead and close this application here. It will stop, and we'll start our whole process here by basically going over to our hard drive, and we'll go into our workspace. One of the things that's been put down here, we made some notes from our boss, which basically output the specifications of the data that we're going to be receiving here. So our goal in our specification is to display heat map data from the VAX. And it's going to be set up as a 16,384 byte array with the values of 0 through 7. So 8 possible values arranged in a 128 by 128 bitmap of sorts, with each number being the color value to display at that location. In addition, we get 3 fields of data that are 80 characters apiece. They're ASCII null terminated here, so it's very easy for our C program to deal with them, containing the heat map name, the timestamp, and the description. And of course, as I said here, yeah, the heat map data is an 8-color plot with legend, and that we want the legend data in its own separate window so that we can deal with it as best as we can. Cool. So the first thing we really should do is actually take and define our data, take and set up our workspace here so that we can actually do this. And the quickest way that we can actually do this is I'll take and duplicate this folder right here. And this will become our heat map folder, because it's already got project files and other things in here that we can use to bootstrap our efforts quickly. Give it a moment to complete, and once we do that, I'll just move it over into place and rename it. Okay. So we'll take and rename, and we're going to call it Heatmap 1, because this is the first pass of our heat map application. There we go. We have our specification, we have our heat map here, and I will go ahead and just throw away this icon right here because we don't really need it anymore. This is the application that we're going to replace. Okay, fine. And now I will take and we will take and rename this to Heatmap 1. Heatmap1.c, and just for the sake of argument, I'm going to take and duplicate this real quick so that we can have a nice convenient little icon to deal with. And this is going to be our .h file, which contains the headers for our structures and other things. And just kind of put it over here. As a matter of fact, I will take and we'll clean this folder up real quick. Boink. Rename. And since essentially we'll be using this going forward, I won't call this heatmap1.h, I'll call it heatmap.h. Again, this is all so that we can easily take and use these files and click into them and bring them right into Emacs, because it has all of our project information set up for us automatically to go right into it. So now we'll just kind of hollow things out a bit here. We got Heatmap 1. Okay, great. And all right, great. We'll deal with that in just a second. Let me go ahead and we'll start here at heatmap.h. And I'm just going to take all this right here and just blast it into space. Here. All right, bye-bye. We will take and mark, actually, let me stop what I'm doing here. I'm going to take and set mark here, boing, and we're going to go all the way down to the bottom. Move down to the bottom, end of buffer, and we're going to take and kill that region just by. Okay. So now with that in place, I'm going to go ahead and split the window in half, and we're going to bring over the data structures from my backup copy here. I'm going to visit the file, EF1. Okay, great. And we're just going to take and mark that, go down to the end. We're just going to move it over. into the other window here. And we're going to take and yank that right in place. Okay. So what do we have here? Well, we have the data structure that we saw before, right? If we take a look at the to-do for the spec, recall that we had 16,384 byte array, value 07, arranged in 128 by 128, and the 380 byte text fields. Those can easily be represented by this data structure right here. Very straightforward. Matter of fact, let me change that right here to match. These are guard statements so that you don't accidentally take and include the same file more than once if it's being referenced recursively or otherwise. So we'll just save that. Okay, there's our heatmap.h file ready to go. We have our data structure that we can use. Now let's actually start moving on to the actual program itself. So, got that. Let's go here. And I'm actually going to be using a similar technique here that I did before, and we're going to take and just to make this expedient so that you don't see me type all this stuff in, I'm just going to take and move the data in pieces over from my backup into the work file here so that you can see what's actually happening. We'll take and save that. Okay, great. Wrote 0 lines. That's fine by me. And we'll split the window again. And we will now visit another file. And we'll say, okay, now we have heat map in mixed low res and high res display. We'll take that, set a mark. And that's just our opening little region here. Escape W, okay. X in and Control Y to yank it in. Heat map in low res, high res display. We'll go ahead and just make that change right there. We know that we want to include heatmap.h sure. And ostensibly, we're going to be reading from a binary file, so it makes sense to go ahead and toss in the standard C functions here for I/O, just for the sake of convenience. We could just as easily take and restructure all of this to use DOS library calls, but really, there's no need to in this case. And we'll go ahead and start building in the includes that we know that we absolutely need. Go into the other window here. We'll start setting a mark for all the includes here. Boom. Go all the way down here for graphics, hardware. And since this is KNRC, as I've mentioned before, these are basically just the data structures. There are no function prototypes because this is KNRC. We'll go ahead and yank those into place. And we will, since we know, now we can actually start building the bits and pieces that we know that we need. We'll go ahead and put in our main function here. There are no parameters here, so we just don't care. But we'll go ahead and get main here ready to go, so that we can actually get something done. Okay, next window. So, what does main actually reference? Okay, so we call init, and if init doesn't work, then we call done. So let's go ahead and get that in place. Sure. Set mark. Come all the way down. Let's copy that in. And we'll go ahead and implement init because we know that we're going to need it. Init is our initialization function, and it will basically just set things up so that we can actually do what our program needs to do. What's actually in init? Let's find out. Let's go all the way back to the beginning here. And let's start thinking about what we need in our init function. Well, we know that we need to do graphics functions, so we go ahead and grab a copy of GFX base. We grab a copy of GFX base. We'll go ahead and set a mark here. And if GFX base, if we can't get it, then we just need to bail. We need GFX base, and we also need a copy of Intuition base because we're going to be using Intuition functions to create our windows and our screens. We'll go ahead and put that in our function right here. Okay, looking good so far. And now we're actually going to need to start building our individual screens. We want to have two screens. So the first screen that we actually want to build here is going to be our heat map. And that's going to come from a new screen designation called NS Heatmap. What does all of this mean? Well, if we actually take and go to our Amiga Intuition reference manual and look at chapter 2, you'll see this is a chapter on getting started with Intuition. And Intuition gives you a couple of sample programs to do things like opening windows and how this is actually going to look, but more importantly, how we take and open our own screen with our own little windows inside of it. It gives you everything that you need to know and to basically set up everything that you need. So in addition to the new window declarations that you saw before, now we have a new screen declaration that gives you all sorts of interesting attributes, such as where the screen needs to be placed, the width and height of the screen, geometry of the screen, the depth, which means how many total colors that all of the windows on this screen will actually use, as well as the default detail and block pin specifications, which colors to use for drawing the screen bar at the top, and the default color palettes to use for all of that stuff, basically. We don't need to use, and after that you have what are called the display modes, which say, okay, is this going to be a low resolution screen? Is it going to be a high resolution screen? Is it going to have interlace, etc.? The screen type basically indicates that whether or not this is going to exist on the W bench screen, which is the workbench, or if it's going to be its own screen with its own modes and characteristics. One that would be added a bit later with version 2.0 of the operating system is the concept of public screens, which is a screen with a specific graphics mode that can be shared across multiple different programs. Whether or not we use our own fonts, whether or not, and the titles and other bits and pieces. So let's go ahead and get our data structure for the screen that we know we want to put into place. Well, first things first, you know that we see that we have here this open screen declaration, and it is returning a pointer to a screen structure. This is not an integer, so it's a damn good idea to basically take and come all the way back and declare an external to specify, okay, that this function is going to return a structure for a screen, and we might as well grab the one for open window as well. Let's just go ahead and get those into the program so that our compiler knows what to return. So expects what to return. We'll copy that and we'll put that into our program. more wonderful housekeeping, but it's KNRC. It's part of the fun of KNRC. And we also need, you saw us take and look for intuition base and GFX base. We also need pointers to instances of those as well. Those will be filled in by the operating system, but we need pointers for them. So let's go ahead and bring those in as well. And just for the sake of argument, because we've already mentioned it, let's go ahead and set up an instance of our heat map data structure. Just call it H. It's there. It'll be ready for us to use when we need it. So, okay. Now we have our first new screen that we're going to take and define. We're going to take, bring that in. We're going to copy that. And this will be globally defined as part of the program here. If we wanted to, we could take and segment this off into the init function, but this makes it easier for us to take and bring it up and then tear it down when we don't need it anymore. But some interesting things that you might see here, and we can compare this with the data structure that we have over here. Look at this. We have start positions right here, a left edge and a top edge. But look at what we have for top edge here. We're wanting this to start 72 pixels down because we want this to show up. We want this to show up at some position on the bottom of the screen here, and it's going to have a width of 320 pixels, a height of 128 pixels. Recall that low resolution is 200 pixels in total, and it's going to have a depth of 3, which gives us a total of 8 colors. We're also going to use colors 0 and 1 in the color palette for our detail pin and our block pin. Nothing special here. We don't have to specify high resolution or anything, so this is a low resolution screen. So by default, Intuition will create low resolution screens for us. We want this to be a custom screen. We don't have any special font that we need, and we want to call this screen Heatmap. And here's the neat thing. You can actually take and create intuition gadgets and attach them to the whole screen as a whole and set a pointer to them right here as the last field in the screen implementation. So that creates our first little screen here. Cool, isn't it? So we got that. And now what we need to do is deal with it. So let me make sure I'm actually in the right section here. We have our screen, and in init, grab our intuition, grab our graphics, and we're going to go ahead and create our heat map screen. Okay, so the first thing we do is we do open screen with the new screen heat map that we did above, and that gets passed as a pointer screen to Heatmap, which is going to contain our screen that we can reference. And we're going to pass that in whenever we take and create windows on that screen. Here we go. Set the mark. We'll take and bring down. Okay, great. Fine. And we will copy that region into our program. Okay, intuition base. Okay, great. And now we have this. This also means that we need a screen instance to hold our heat map. So let's go ahead and put that in there just to put it in here. Heatmap. Let's do that again. We can see, okay, we have a struct screen for Heatmap. Groovy. That needs to go up here in our globals. New screen. So let's say struct screen. S Heatmap. Groovy. Okay, so now we have everything that we need in order to make our particular little program here. Okay, great. That's cool. And just for the sake of argument here, what I'm actually going to do is make a little delay. Same thing here. If you saw our getting started with intuition here, we're just gonna take and do a little loop that just waits for a bit. Just nothing. It's not going to do anything, but we're eventually going to take and just close the screen as part of done, right? Well, what's done? Done does the opposite of init. And if we look at what we have in our main program, we take and if we have our heat map screen, we take and close it. We also take and close our intuition base and our graphics base. So let's go ahead and get that in there too. Make sure that anything that you open, you close. You make the mess, you clean it up. Mom's rules. Let's copy the region. Put this in here. Okay, great. So now we kind of have everything that we need here to show the first phase of our program here. Groovy. Let's take and write this out. Now, while this is happening here, we will take and go to my system here, open up our trusty little command line interface. Go to our workspace. I thought I was in Unix for a moment there. We'll delete that sign.o because we don't need it, but it's not part of our, wasn't part of our workbench, so we didn't see it. There we go. And we'll take and build our application. Oop, sorry, forgot. It's been long enough that I forgot that you don't use the .c. That's okay. Rather interesting there, redefinition of preprocessor symbol. No, it's not going to have an effect on what we're doing here, so we should be okay. Oop, undefined identifier I. I can fix that. Let's go ahead and go back in. And let's go to line number. In fact, I know where this is. It's right here, and it's because I'm an idiot. We'll temporarily define this here. Save it. And go back out again. Let's try that again. Oops. While this is happening, it's definitely a good thing to take and thumb through the intuition manual here. This was written mostly by R.J. Michael, who wrote this as part of the documentation process for documenting intuition in the first place. And he uses a lot of different examples for doing things such as building windows, building screens, and the things that you can get away with doing. And you can see some of the interesting things that make intuition a bit different from other menuing systems at the time here. You'll notice that menus can not only contain textual things, but they can also contain images as well. He's got an eyeball right here. You can see some gadgets such as a proportional control right here, down here as well. Sure. And if you look close enough, you'll find some interesting things, such as the fact that this is using a pre-release version of the Workbench here. Version 2931, an interesting little bit of archaeology here. But yeah, this was our first manual for dealing with intuition. You'll see all sorts of different things, such as building managed custom screens, different screen characteristics, such as the display modes that you can mix and match, and how these things relate to other graphics library conventions, such as gels, which are the graphical animation elements as well, a listing and a mention of depth, and so on and so on. And you start to see examples of taking things and putting text in windows, and an important talk about screen positioning, such as height, width, starting location, etc., making an important point that there are acceptable placements of screens where this screen is directly in front here and it's nice and horizontally separated, while this screen is not. This smaller screen cannot float in front of another screen here. They have to be anchored to the bottom of the display, as it were. It's one of the interesting quirks of intuition and how it sets everything up. But there we go. So we have Heatmap 1, and if we take and run it now, we'll see that we have now created our first little bit of our display here, our heat map, which this will go away in just a moment. Okay, great. So now we've seen that we have our, now we see that we have our little screen here, and you can see that it's creating that screen with the default color palette and placing it directly in front. And this screen can be moved up to this point. It has that maximum size. It can be moved behind other screens as well. All the depth and everything works here. And see, it's already gone now, and so on. So again, this is just something that the Amiga hardware does by default, and it's really cool. So now that we've done that, now we can take and start building up the bottom part of that display right here. And we'll start that now. So now that we've created that, the first thing that we know that we need to do is we want to take and create a window to hold our heat map display, and that will actually contain our close widget for our program. So for that, we'll need a new window declaration. We'll go ahead and grab it from our program. New window, and this is our heat map window here. It is, and if we'll take a look, we'll get a good look at it here once I take and mark it and move it over. Copy that region, and we'll move it over. So here we go. We got new screen, got heat map, and we have a corresponding window or heat map here. Now this particular window is actually going to start on the left-hand side of the screen. It's going to be 128 pixels across, 128 pixels down, using the same detail and block pins as are defined by the screen here. It's going to have a close window gadget that we are going to react to. So we have our IDCMP for close window and our corresponding gadget right here for window close. And this is also a gimme 00 window, which means that it's going to take, Intuition is going to take and render the window border and the contents of the window separately as separate layers so things don't spill over. Pointer, this window, ironically, is just going to be used for visualization, and right now, as of this point in time, is not going to have any gadgets inside of it. There are no user gadgets or user checkmarks, special checkmark graphics for the menus. It's going to have a title called Heatmap. There's no super bitmap. And we have an explicit sizing limit of 00, 128, and 128. And because there's no sizing gadget, the window is basically going to be static. And because we're not allowing the window to move, once the window has been placed, it's just going to be there on screen. So how do we get it in place? Well, that's easy enough, isn't it? We'll just take, and as part of our initialization here, we have our screen, sure. And we will take and place our window. Do that again, do that again. So here we go. So we have NW Heatmap. And as part of building this particular structure, you'll notice that there was actually a blank area in the new window declaration that points to what screen we're going to be placing this on. Because that screen is not statically defined, it cannot be statically defined, we have to actually take and create the pointer to our created screen after the fact. So we take the opportunity to do that after the screen has been created. We'll go ahead and do that now. Then we'll go ahead and immediately start building our windows. The first window that we need, well, I'm going to go ahead and I'll put the legend in here in just a moment, but for now we just need to implement, say that the screen for the heat map is going to show up on our screen that we just created. We have W legend, we have W heat map. We'll go ahead and do W heat map. Okay, great. Sorry. Set mark. And we will take and copy that region, bring it in. Boom. And as a matter of fact, we'll go ahead just as part of building the window heat map here and window legend, we'll go ahead and the window legend, we'll go ahead and just put that in there as well. So we'll go ahead, come back in here. We have W legend. And this is much the same thing here. Set mark. We'll go ahead and copy that region in. Heat map. W legend. Okay, great. Boom, boom, boom. And we know that we need to create structures for those so that we can reference them. Sure, no problem. We have struct screen, struct window, struct window, W legend. We'll go ahead and put those in, make sure that they're here. And just for the sake of argument, we'll go ahead and put the new window in for the legend as well. Because compile times are long on this system. And I don't want to take and bore you guys too much. So we'll take and NW legend. and bring this over. Copy, read, set mark. Copy region. And no comments over here, but you'll see some differences, particularly where this is positioned relative to the other window here. It's going to be placed to the right and just a little bit down so that we can see the window title. It's going to be placed, it's going to have 100 by 114. We're going to go ahead and put this on the backdrop for different reasons here. So this gets rendered as part of the backmost part of the screen. Temperature scale, size, etc. Okay, great. We'll see how this looks in just a moment. So let's go ahead. Construct window legend. Okay, great. Now NW legend. Okay, created the new windows. And one of the things that we know we need to do here is what I removed before. This needs to also point on legend so that legend shows up in the correct place. So now we've created W Heatmap. We've created W legend. And now if we actually take and this should be sufficient, hopefully. Actually, I need to make sure that we now take and close our windows. If this is just so we don't leak anything. So now we've got our open and our close. Okay, great. This is doing good. We're still using our dummy loop here. We'll put in an event loop soon enough. Save this out. Let's see how this builds. Oops. Definitely one thing that I keep forgetting as I'm using different operating systems is the peculiarity of Amiga DOS to differentiate the execution of scripts and the execution of executable programs. For scripts, you have to use the term execute. At least you can put the scripts in your S folder so that Amiga DOS will look for them there by default. So you don't have to type a whole path to them. Let's see, is there anything else we can take and talk about while this is going on? You can see some of the other view modes, etc., that define what you can do in Intuition. If you want high resolution mode for a particular screen, you have to define it using the high res keyword here. We're actually going to be doing that for the description here. And if any of your displays need interlace, 400 line display, then you need to take and set interlace as well. You also should tell Intuition whether or not you're going to be using sprites. If you want to take and utilize the dual playfield mode of the graphics library and the graphics hardware, you can put it here. And for applications that need the hold and modify mode, which can give you all 4096 colors of the Amiga at once, you can set the ham flag. And believe it or not, okay, you can see set this to custom screen. And there are a couple of other flags that are defined in Intuition H, and one of them is custom bitmap. And you can literally use this if you want to take over the entire screen's display as a super bitmap to display from elsewhere. You can do that just by setting this here and making sure that you define a pointer to a bitmap structure so that Intuition can take and set up all the pointers and stuff in the copper list appropriately. So now that we've got that here, we should be good to go. And let's take a look and see let's look at our damage here. We can start to see our application take shape. We've got a closed window here, which is not reacting to any events, but we have our two windows here. One for the output and one for the scale. Okay, great. Now we can actually start doing some interesting things, can't we? Let's take and complete our screen layout by taking and building our high resolution display. So with that, we go ahead and go into our display here. Okay, great. God, I wish I could just take and tap the mouse to take and select the other window here. That wouldn't come until a bit later. Anyway, so there's our heat map. Go into our original window here and come up to the top, and we'll do NS description. This is our new screen description for our description window. And as soon as I take and copy it over, I'll take and talk about for a moment the differences between the low resolution windows that we have been making and what this one does. Set a mark. We'll go ahead, copy that region, bring it over. NS heat map. Yep, here we go. So we'll just put this here because we can. Why not? Let's yank it here and have a look. This is its own screen here, and it needs to be its own screen because, again, this has different resolution characteristics from the other things that we're displaying. One of the things is that this screen is 640 pixels across. It is also 200 pixels down. And the reason for that, there's going to be some interesting reasons for that. This is going to sit on top of our heat map here. And if we were to say, well, actually, this only needs to be, say, 128 pixels down below, you're going to run into some interesting peculiarities because Intuition is still going to try and fill the gap for the screen data underneath anyway, and you might get some random bits of information of data sitting in memory to produce some rather strange things. So to prevent that, we're going to go ahead and allocate an entire high resolution screen to sit behind our heat map. Since this is a high resolution screen, we need to set the high resolution attribute as we saw in the manual earlier. This is a custom screen, again, null. This particular screen is called description here. Okay, great. Let's go ahead and get this sucker going. All we have to do is open a new screen. That's all we got to do. Let's just take and move it over. S description. Okay. Well, we know we need the screen definition for our description. Let's move it over. Sorry. Set mark. Oops. Set mark. And so struct set heat map, struct screen. I'll go ahead and just put this down here on its own. Struct screen, S description. And as part of that, we need to actually define that screen, don't we? Using the same exact method as we did before, using the open screen command. Okay, so we set our mark. The reason I'm using the menu option here to do this is because I can't type this particular command in the simulator correctly for one reason or another. So I have to take and do that from the menu. It's not the worst thing in the world. Let's copy that region over. And just come down here to the bottom here. Yep, we got it. We got it. There's our window. There's our legend. Okay, great. We'll go ahead and implement our description screen. Okay, again, open screen, could not open description screen. And that's everything that we need to do in order to take and build our secondary layer here. Go ahead, save that out, and let's have a look at it and see what this looks like so far. So, just make sure that I got everything. And again, there are, if you look at the back of the manual, you'll find all sorts of information on the different functions that are available and what all they can do, because there are a lot of programmatic functions in Intuition, such as being able to take and show the screen title bars. You can programmatically move the screen, change how the screen is moved in relation to other screens as well. So you can take and arrange things programmatically as you want them as part of your program design. Of course, you can close the screen. And rather interesting enough here too, you'll see that there's a section called Handling the Workbench. And on low memory Amigas, this was absolutely important, because the workbench, if you would close the workbench, you would get on average about 32 to 48K, maybe even more, of available RAM back to you, which on a 256K Amiga is a godsend. So you can close the workbench to gain some memory and open it back up when your program finishes, and so on. You can also take and reorder. I mean, you can immediately bring the workbench to the front or the workbench to the back. It's very nice. There are advanced functions here where if you want to take complete control of how screen handling is done in Intuition, you can quite literally take and pass you can call the make screen functions directly, which you can alter how viewports are created, that sort of different things. And you can, if you really need to, if you're messing with Intuition data structures directly, you really shouldn't, but they're there. You can recall rethink display to have Intuition figure out which order layers and things need to go in, that sort of thing, of course, and remake display to take and draw the results of what rethink does. They're there, and I appreciate the fact that RJ put them there, because somebody might actually need to do it. So, interesting thing, you saw what happened right there. It created our high resolution display, and then kind of and then it did this here. Okay, great. So it put it there, and because I didn't destroy it, oops, that screen is now leaked here. So there's a couple things that we absolutely need to do before we go on. The first thing is we want to take and do a slight reordering so that our description screen is done first. We'll take and mark and move, just do a little mark and move. We'll copy that region, and then we'll actually Control W that whole freaking region there. And we will move it up here. So that little bug right there shows you that creating layers is important, because it can make things easier for you later. So otherwise, if I didn't do this, I would have to reorder, to use those functions that I was just talking about, to reorder the screen so that they're in the correct order. The other thing that we need to make absolutely sure that we do is that, again, You make the mess, you clean it up, because intuition is not going to do that for you. We'll go ahead and do that. Now, we are, since intuition has, since we have this screen that's just kind of floating here in nothingness and nothing's really attached to it, it's kind of orphaned. The only thing that we can do at this early stage in Amiga DOS's evolution is to reboot. So I'll go ahead and we'll just do that. Excuse me for a moment. Oh, come on. There we go. Good thing is that unlike your typical Unix workstation, Amiga DOS boots up pretty quickly. And it would boot up even quicker once we were able to take an auto boot from the hard drive. We're still having to boot from floppy here, but that's okay. Even booting from floppy here, this isn't too bad. We're up and running in just under a minute. There we go. So now we've got this here, we got an NT disk here. Let me go ahead and just bring all this back together. We made our little mistake here, so while this is going on, I'll go into the workspace. We'd made our little change here. We'll go ahead and get this guy building while we've set the rest of the system up here. Sure, why not? Boom. Okay, so go back into our workspace. There we go. Heatmap 1. There we go. Running snapshots a good thing to do from time to time. Again, this is a 68,000 base machine. I'm doing a compile of C code back here on the back, and it's just taking it, man. X2, we'll do an XV. We go right back into Heatmap C, and that'll get us ready for the compile to complete. Okay, ready to go, and we should be pretty good to go here. Okay, phase 1, phase 2. The intuition manual goes into detail about opening, creating, and activating windows, and we also get a number of what are called special window types, such as the borderless window type, which this is a window that has a content area but does not have a border. And the other being the Gimme 00 type, which I talked about earlier, which allows you to when you draw into a Windows context, it gives you the content area of that window as 0, 0, and it does this by creating 2 separate layers. It warns you as part of this whole thing that if you start building multiple Gimme 00 windows on screen, your display performance may suffer because of all the layers that Layers Library has to create as part of the process. It makes a few notes here, basically stating that the console device is one of those cases where you don't need to use Gimme 00, and other bits and pieces too. And of course, the backdrop window type, which we touched on for a moment earlier, which allows you to put windows and content on the backdrop of the screen in the rear of every other window that could potentially be on screen as well. Use that for, say, the main parts of simulation code, like what we're doing here, and so on. And of course, the ever-present super bitmap window, which you can use to basically take control of window rendering entirely on your own behalf. And we can see right here, now we've got everything in the right order. We have our heat map, we have our temperature scale, we have our description screen here. And all we really need to do here is add our window for our description screen here And we'll have all of the content areas that we need in order to actually start drawing into our window. Isn't that great? Yay, okay. And we might as well, I think we might as well, just as part of the process here, we might as well, since we have the data file, let's get the data file in place so that we can just start, rendering data. But first, let's put the window in place. NW description. Again, we have our window for our description right here. Set a mark. This is our description window. We're really not going to see the title for this because it's going to be backdropped. And so the screen bar is actually going to be in front of it. But that's okay, I guess. We'll take an NW. NW heat map. So there's a struct for new window. There's a struct for the description screen here. Nothing really special here. It's just, it roughly represents the dimensions of the screen that we set up here for what's going to be visible. And it's going to ultimately contain our description data. But we need the window in place. Let's go ahead and get to here. And we've got our description window. And as part of that, we know we absolutely need, there's our description screen. So now we can start putting in NW description that we just defined here. Screen. S description. So again, the same pattern that we had before. NW heat map, attach it to the screen so that we know that we render to our screen correctly. And we go ahead and output our window. Okay. So all we really have to do here is deal with our W description. We need it, so we'll go ahead and put it in here. We'll put it nearby, okay. W description, there it is. W description, W description, W description screen, okay. And there we go. So let's take and grab that over. Set the mark. We will copy that over. So W legend, we'll just, W legend, just down here. Okay. So if we come back up here to where we've defined our description screen here, we can put our window creation code right here. And there's our window. And it will be, since this is rendered as a backdrop, we'll actually have it in the back of all of this. So it will be that window will be in the back. You recall that when we ran Heatmap 1 before, it created the window description here, but there's no window border for that window because there's no window here yet. So that window that we just created will actually provide the space for us to draw into. There we go. If we wanted to, we could create a borderless window and not have that window border there, but I want it there. So let's just move on. Okay, so now we have that in place, and just for the sake of shits and giggles here, we're going to go into init, and we're going to take and load our data. We're going to acquire our data. And the acquire section for our data, because our data is in exactly the right format that we want to be able to use, we can f-read that data right in. Just a nice, simple binary read. So I will go to acquire, and we will grab this function wholesale. copy that region here, and we will put it just above our main, like we have it here. And we will take and make a little call to it down here. Acquire, sure. We'll just take and acquire the data. All right, it's done. Okay, fine. We'll just acquire the data and get it. We'll get the data in place so that it's there when we actually want to start using it. Okay, great. Well, let's start taking and populating. Now that we've got our windows and everything in, now let's go ahead and start populating the data inside our windows here. Well, we can start with our description. The description is going to be real easy. We'll make a little function called description here. Okay, let's just pull it in as it is. Of course, set mark. Let's just pull it in. There's not much to it. Copy that region in. And we'll go ahead and just call it here, because we'll have the data. We might as well display it. And put our description function right here. And you'll see there's not much to it. We have the data. What we do is we take and set a particular pin that points to our description Windows raster port. We want to set that particular Windows pin to 1, so it gives us the white color. And it wasn't, I didn't really specify it, but the description window, since it only needs to display text, I'm being as memory efficient as I possibly can be, and only specifying that that window is 2 colors, that has 1 bit depth. 2 colors, foreground and background. So we basically take and move our raster port, put out the text. That's it. And text only has a couple of particular parameters here. These are calls into the graphics library. So we say we get the raster port, we get the data, the text that we want to put in. This is, and we specify it. We have to specify the length of it, so we just get Sterling to get the length of it. We do a little math here because I've kind of fudged things across so it's nicely positioned inside the window here. But since we're using Gimme 00 windows here, these are 0 coordinated windows that correspond to the top edge of the content window. So there you go. There's our description. Let's go ahead and put that in. And this will allow us to test whether or not the reading of our data is going to work as expected. We'll go ahead and build that. And while that's going on, I'm going to make double sure that we actually have a viable, that we have our HDAT file. We should, but I'll make sure. Again, multitasking power. I can open another CLI window. Sure, no problem. Let's have a look. Do we have our data file? We do not. So it's a good thing that I brought this over because I need to take and copy it. I'll take and copy that in from... Copy that over while this is taken care of. And we have a compiler issue here. Ooh, what happened? Let's see what happened here. I will take that and just kind of put that off to the side here for a minute while I look here. 93, 94, okay, duplicate, all right. What happened? Just a second while I take a look. 73, declaration of expected. That's in line 92, 93. Let's have a look and see what actually, where this happened. I'm guessing this is the window declaration that we put aside here. Let's find out. Go to line. Okay, so this is there's something goofy going on here. Okay, struct new window, NW description. Okay, so something's not something, it's not happy with something here. Let's find out. Okay. Let's do it again. Make simple duplicate declaration of item description. Okay, let me take a look at that one real quick. Duplicate. Did I accidentally put description in here twice? Oh, oh my! I did, didn't I? That's a mistake, but I can easily get rid of that. Wow. My bad, huh? All right, just bye-bye. Kill that region. So we'll save that again, and we'll see what happens. While that's happening here, we'll take an execute and make simple heatmap 1. I dropped a control character, it seems. Let's see. And as a matter of fact, I'm going to take and expand this a little bit more. And when the error actually starts to happen, I will take and hit the space bar right here to stop the output from the compiler so I can see what's going on. Oops. Duplicate different. Did I? Oh, that's what happened. Okay. NW description. All right, got it. We can fix that, can't we? So, fine by me. Where did it say that started off at? Duplicate definition, line 83. All right, let's have a look. That may have been just a stupid mistake on my part. Probably was. 83. So, NW description, new window. Ah, it was. Oopsie. Wow. How did I duplicate that twice? If somebody can wants to, they can talk to me in the comments and tell me what I did to accidentally duplicate that. Oops. Okay, let's just kill that region. Fine. Fine. What? Can't open. Huh? What? Oh, it's because, okay. It's because the compiler's still running. Oops. Okay. My bad. Let's save that again. Let's try that again. Oh man, that's just great. File was open. File was locked. Okay, let's try that again. Execute make simple heatmap 1. And the nice thing is, as we start to do more of these applications and we work through adding functionality and things that we need, we're going to delve into doing things like making custom gadgets for our application here. This is merely the first pass to basically show that we can do these things and to prove to our boss, little bit by little bit, that this machine that we're using here is efficient and is going to save us time and money. And that's how the Amiga got into all of these little areas of and places doing secret things, basically just you know, we run out of budget, and oh crap, okay, well, turns out, well, we can't spend $40,000 on a brand new Sun workstation, but we could spend a couple $1,000s to get an Amiga, and you know, take that out of the petty cash, and or potentially take and spend a couple $100 on getting some boards made to connect to the Zorro bus to do DMA transfers. Those sorts of things were altogether very common in engineering shops. Okay, apologies for that. I had to go take care of something real quick. Okay, the compile has completed. Let's see what we're looking at. Okay, so something not quite right here. I'm guessing we're probably not calling description. Let's just see what happens. Yep, let's see if we can fix that. Let's see. So a couple things we know we probably need to do. W heatmap, W legend, okay. Let's go ahead and add W description. W description, okay. And let's make sure, as part of our window here, that we're actually, after we're calling acquire, that we're actually filling in the description. We have the description window here, okay, acquire, and description, okay, great. Let's make absolutely sure that we have our data file. Oh, opening H file. Okay, so that I need to copy that from to here. One moment. Yep. Sorry, having to take care of other things. But if we actually take and do a directory here now, we copy this in. We've got our heat map data. Why are you not showing up here? Copy the file. There we go. Let's have a look. HDAT. Okay. And if we list the directory, oh, yeah, what's the directory? Weird. Okay. Never mind. 16,624 bytes. Anyway, so that gets set. Now if we run, we see our description, and it's now being plotted up in the description window. Now we need to take and fill in the bottom sections here, starting with our temperature scale. And as part of our temperature scale, you'll recall if we ran the program at the first of the video here that there was a color palette change. Well, we need to actually take and implement that color palette change. And we'll do that in our legend function. If we come back, we'll come back here. And we see our legend update here. Great. Groovy, groovy, groovy. We'll take and set mark. And this will draw the individual legends that we need. And the way that this actually works, you'll see that we have a whole set of text objects that we basically fill out in a loop, where we do the same thing over and over 8 times. We set a pin to draw our rectangles, which will take and show our different legend chips so we can see the different colors. These are 8 pixels wide by basically 8 pixels deep, with a little bit of a shift in horizontal position so that they get pushed into the right place, and vertical position so that they get put in the right place. And then finally we take and move, set the color of our pen to our text color here, and then draw our text for each element of the legend based on these elements up here in the array. Really simple. So we do that. Okay, great. Let's go over. I think I brought it over here. Oh, nope. Let's not do that. This is our previous kill buffer. Just kind of kill those lines here and do this again. Set our mark to our legend, and we copy the region in. Again, same technique as before. Boom. And then we'll go ahead and just call that as part of our acquire, description, and legend. You'll see that as part of the legend here, what actually happens, again, we are, in order to make sure that we call into the right window and do the things that we need to on our right window, every single window that gets created has a raster port. And this is equivalent on other platforms as the device context, the DC, the device context, that sort of thing, the graphics port, depending on the platform that you have here. And it just points to all the bits and pieces that the graphics library needs to know where to take and do its graphics information. So, because each window has its own raster port, if you pass that raster port into each graphics function, it will make sure that it does the correct graphics operation for the correct window. Okay, there we go. We've got that in place. And we make sure to call our legend in our main window here. Go ahead and save that, and we'll build it. Now, let's go ahead, make simple Heatmap 1, and see what we got here. One of the important things that actually gets brought up as part of designing intuition windows, and I actually brought this up in a previous video with the sign demonstration, is that intuition has the ability to actually take and handle window refresh for you in a couple of different ways. You can either choose to use a simple refresh, in which case your program handles all of the drawing inside of the display. Basically, you figure out what needs to be changed, what needs to be refreshed, you do the refresh, and then you bounce back into your main loop. Intuition, however, can keep copies of the bitmap of the window in the main memory, so that as layers get moved around, the individual windows and whatnot, Intuition can restore those things from the backing store that it creates. That's the smart refresh method, and it is what is used by Intuition Windows by default, which is a nice thing because compared to other graphics platforms at the time, such as GEM and Windows and Mac OS, you had to handle redrawing your display whenever parts of your window would be occluded. Because Intuition was built on not just the graphics library, but a layers library that could keep multiple stacked layers in order and draw things in the appropriate areas. And you could combine that with the ability of saving a backing store for each of these layers and whatnot to drastically simplify the refreshing that you need to do for a particular window. Okay, linking is complete. Let's see what we got so far. We should have a legend display on the right-hand side, but we're going to know something very interesting about that legend display. It's going to be using the default palette that is set up by the operating system. You'll see right there that we have a temperature scale. There's 8 colors here, and these are the default. This is from the default palette that gets set up by the operating system, but we can see our temperature scale is there, and it works. It's great, isn't it? So now we've got our description, we've got our we've got our legend over here to the right-hand side. Now all we need to do is implement the part that draws the main part of our display, and we'll have all of our drawing stuff in order. I'm doing all this in a very specific order here. Don't worry here. I know some of you are screaming, what about the palette? We will get to that. Don't worry. What about the palette? What about the event loop? Those are the last 2 things that we will do. So next, we're going to go ahead and actually implement the heat map itself. And all the heat map has to do is scan through the bitmap that we have loaded in from the data that we got from the VAX and plot that 1 pixel at a time to the display in the appropriate order. And that is done in this function right here. We'll take and mark it and bring it over. Mark it, yank it, bring it over. It's just a set of interlocking loops here. Copy the region. Okay, great. And we'll see that all this is, we set up some counters and we have an offset into the buffer that we're dealing with right here. We just make this really simple. We get our data as one big one-dimensional array that we can just scan through. We don't have to scan through it in any particularly strange order. So it makes sense for us to basically treat it as one big one-dimensional array that we unroll into 2 separate loops for the X and the Y directions. And for each, we figure out the color that's actually in the particular plot in the H data. We set that to the pin for the raster port, and then we use the graphics library write pixel function to take and write that out to the display at the appropriate X and Y offsets, taking and increasing the X offset and the Y offset, resetting the X offset to 0 when we reach the end of a line. That's all we got to do. So we'll go ahead, got that description, legend, and we will plot the heat map. Okay, written 307 lines. Let's have a little look at this. Take and execute, make simple heat map 1. And again, so like I said, with the combination of simple refresh here, it goes into the description of how simple refresh works, the obscured portions of the windows discarded, that sort of thing. And then you've got smart refresh, then you've got obscure portions preserved off screen. And so whenever this comes back, you'll see the exposed portion coming back into play. And finally, super bitmap, where you have an off-screen bitmap that you use as your source material to draw into the target window. Really great for scrolling regions and the likes, like maps and the like. It's really, really cool. It becomes very easy to take and deal with the window display with these particular refresh methods. Window colors, window dimensions. Let's see, what else? Anything else we want to take and cover while we're here? Eh, not really. You can see some of the different window flags for things like gadgets. So you can add things like the individual window gadgets for setting window depth or for resizing the window, such as this resize gadget down here. Whether or not this window should take and report its mouse movements via events, that sort of thing. Whether you want to trap the right mouse button so that you can do your own operation in response to the right mouse button instead of displaying the intuition window, and so on. A lot of thought was really put into this API. It's very impressive to me, literally, how much time and energy was put into making something that would both be very consistent, but also very distinctive for those that wanted to make a very distinctive user interface, but still be consistent in the context of all the other Amiga applications. I think it was a nice balance. Here we go. Linking is now complete. Our binary is at approximately 31K at this particular point in time, but now if we take and run our heat map, we should now see our heat map display starting to come across. And there it is. Most of our application is pretty much complete at this particular point in time, but there is one thing missing. You'll notice that all the colors are wrong here. We really need to put meaningful colors in here. And for that, we'll actually take and put in and set our palette in our init method. Watch this. So to do that, we need to go back to our init method. And if you look down here at the bottom of our init method, after we have created all the windows, made sure everything's nice and neat here, we then immediately start setting a screen palette. Now here's the interesting thing. It's another reason why we actually used separate screens for all the information. Because as it turned out, the color palette, the default color palette, is good for displaying text. It's good for displaying high-resolution text information. We don't want to mess with that, but we do want to take and have our own color palette for the heat map information so that we can take and use a color set that makes sense, ramping up from green to red and having blue for areas, having white for very hot areas and things that we don't care about. And because of how the Amiga actually works with its copper chips and everything else, each and every you saw at this first of the video, each and every scan line can not only have its own graphics mode, but it can also have its own color palette. This is just part of the hardware. It works. And for us to do this, all we really have to do is call graphics library, pointing to the viewport that our screen has set up. Since we're dealing with the screen, we're not dealing with a raster port this time, we're dealing with a viewport for the particular screen, and we set each color element. And for that, we go ahead and bring this over. And for the sake of it, we'll say, okay, yeah, we're going to set a loading message. Sure, why not? Because why not? It's already here. We'll just take and bring this over. We'll copy that region over. Let's just copy that. All right, let's just and init. Come all the way down, past all the creation here, and set our color palette. And we'll talk a little bit about the parameters that the set RGB4 actually takes here. We can kind of see it here. Okay, setRGB4 is a method inside the graphics library. It needs 4 parameters. The first parameter is a pointer to the viewport for the screen, for the particular screen in which you want to change the color palette. We want to change the color palette to the screen that's on the bottom section of our display. So that's its viewport, Heatmap viewport. And yes, sorry, 5, not 4, but 5. The next parameter is the color index and the palette that we want to set. Since we're dealing with an 8-color display, these are color indices 0 through 7. And this is followed by 3 parameters which correspond to 4-bit color values. So that's 0 through F for red, green, and blue, respectively. The first color is color 0, and that's because we've defined the screen to use the default color pen here. That's going to be the background color 0, so we set that to 0, 0, 0, which is black. We then set the next color here, which is color 1, to a moderately bright blue color. So that is 12. Yeah, 12. Then we start ramping up for the individual green colors that we know we want to use. We want to use 3 green colors here to represent good color ranges that we want to say are within heat tolerances here. So we set those to 8, 12, and 15 respectively. So a dark green, a medium green, and a light green here. And then we take and set aside 2 colors on colors 5 and 6 for our red. These are colors that we want to pay attention to, potential problems. And finally, we want to set color 7 here, turn all of the bits on for each red, green, and blue, and make that a white color. So with that in place, and with the loading message that we put down here at the bottom here, we'll wind up with something like this. Let's see, let's go ahead and build it and see what we got. Some of the other things that you can do, which will be useful, we'll do later on, is we'll do things like setting up a custom pointer. Let's say, for example, we want to change the shape of our mouse pointer here to be a set of crosshairs. Well, we can. We just have to create the appropriate sprite data structure, and we have to call setPointer to take and use that data structure. And it gives you some notes down here at the bottom that say that there are additional constraints that are imposed on that image structure. Image is used for both both bitmap and sprite data. It's kind of nice, and Intuition takes and abstracts that quite nicely so that you can interchangeably use those things in those 2 contexts. So it gives you an example of how to take and do a custom sprite, converting that into 16-bit bitplane data, and then showing the result. And I hope going forward here, we'll actually get into the whole process of taking and making gadgets. Gadgets are absolutely wonderful in the context of Intuition. Intuition actually takes and manages the drawing and the state and the manipulation of those gadgets as part of its primary process. So the gadgets are always responsive, even if the program is not. It can make things kind of unusual because you can see, oh, the button will click, but the program may not respond. And that's ultimately why. It's because Intuition is actually handling the drawing and the state manipulation of those gadgets. It's part of its process. But Intuition makes it possible with a handful of simple gadget types to take and make things that you can interact with, and do so very easily. And now we're done here, and let's see what Heatmap 1 looks now with our custom color palette. We're going to notice that as we run this here, because we've done that second screen on the bottom, it can have its own color palette, and it will match the data that we need for our heat map. Ta-da! So now we have our nice description up top, and we have our heat map data down here at the bottom, looking all nice and pretty with their own color palettes, own resolutions, and what makes sense for the target program. That leaves us with the final bit of program code here, and that is basically just to handle the event processing for the close button. And that's simple enough. You saw kind of what we did for the sign program. We'll do something similar here too. So let's go ahead and do that. All we really have to do at this point, come back down to main. We got heat map, and right now we've got this loop here, which is just keeping the program open just long enough for this to run. Let's get rid of that and replace that with our little event loop. And all we really have to do, again, since we're really just looking for that close message, we just spin ourselves in a wait message, grab the message for what's coming in, we reply to it, and if it's a close window, then we take and break. That's all we really have to do. So let's go ahead and just pull that in. Let's take and set mark. And we're looking at it. Remember that the close is attached to the heat map window, so that's where we're looking for that event for. X in, push that here, and with all of this, we'll compile one final time, hopefully, with our completed program. A couple of you have been asking pretty much as I've been doing these, if I'm using some sort of script. No, really I'm not. I'm literally doing all of this on the fly. I'm recording all of this in one big shot on the fly, and basically everything I'm talking about, everything that I'm doing is coming out of my head in the context of all of this, and I'm keeping all of this in my head as I'm doing it. As such, if I forget something, don't hesitate to leave a comment, and I can try to address it in the next video. Looks like we've got a little bit of an error here. Okay, 324 and 333. Okay, no reference to identifier I, so I can fix that. Those are warnings, so let me take a look real quick and see what we can do here. Window, go to window, go to line, 324, which is, yeah. Okay. That was what you were mad about? Okay, 324. Pointers do not point to same object. Well, okay, that's fine. And 333, no reference to identifier I, which is basically just saying it's that I variable that we put together here that we're no longer using because we're not using that for loop. I can just as easily take that out, but there should be no reason to have to recompile that. We should be okay. Let's look and see what that's talking about, 324. Window, go to window 324. Reply message. Okay, fine. Do not point to same. I don't know, whatever. I think that's okay. It's in my original code and it works, so it should be fine. If this is incorrect, please let me know. Again, it's been a while since I've done all of this stuff, and I'm dredging this stuff out from the recesses of my mind. Okay, 31,536, looking good so far. And let's have a look. Heatmap 1, we've got a draw with our two screens, high resolution on top, low resolution on bottom. It's now sitting there waiting for a response, and we can take and move. You can see how the different screens are put together here, and move things in and out of the way so you can look at other things potentially on the side. And when we're done, we can hit the close button to get out of it. So there we go. We've created our little heat map application, and it works. And it only took us just a little while to do it. So now here's another thing we can show to the boss to actually take and prove our points. So in the next sets of videos, I'm actually going to think on what I'm going to deal with next here, but the general direction is we're going to be taking and refining this program and adding features to it and making this program as useful as it possibly can be. So until next time, guys, have fun.